Welcome to my sleep science channel. Tell me where in the world you are watching from. And as the evening settles around you, allow your thoughts to drift gently toward one of the quietest mysteries in the universe. Tonight, we begin a long journey through the smallest stars that fill our galaxy. Stars that are so common that they quietly outnumber almost every other kind of star in the night sky. They rarely demand attention. They do not shine with the brilliant white light of our sun, nor do they explode with the dramatic endings of massive stars. Instead, they remain calm, patient, and incredibly long-lived. They simply continue shining for trillions of years, offering countless opportunities for planets to orbit them, and perhaps for life to appear. When most people imagine a star, they picture something much like our own sun. Bright yellow light fills their imagination, warming nearby planets and illuminating a familiar sky. Yet our sun is actually somewhat unusual when compared with the enormous population of stars spread across the Milky Way. Most stars are much smaller, much cooler, and much dimmer. These are known as red dwarfs. If you could somehow travel across our galaxy and visit star after star, you would quickly discover that red dwarfs are everywhere. They quietly dominate the stellar population, making up roughly 70% of all the stars astronomers have identified. Every patch of the Milky Way contains countless examples, many so faint that they cannot even be seen without powerful telescopes. Their small size gives them remarkable stability. A red dwarf burns its hydrogen fuel very slowly, while our sun is expected to shine for around 10 billion years before changing into a completely different kind of star. Many red dwarfs may continue shining for hundreds of billions or even trillions of years. This number is almost impossible to imagine. The universe itself is only about 13.8 billion years old. Not a single red dwarf has yet reached the natural end of its life. Everyone that has ever formed still exists today, continuing its quiet work in the darkness of space. This incredible lifespan naturally raises an interesting question. If life requires time to develop, perhaps the longest living stars provide the greatest opportunities. On Earth, simple life appeared relatively early, but complex organisms required billions of years to evolve. Forests, animals, oceans filled with fish, birds flying through the air, and eventually human civilization all emerged after an extraordinarily long process of gradual change. If a planet around a red dwarf remains stable for hundreds of billions of years, evolution could have far more time than it has ever enjoyed on Earth. For many years, scientists believed that these small stars were probably poor homes for life. Because they shine so faintly, planets must orbit very close to receive enough warmth for liquid water. Such close orbits seem dangerous. Strong bursts of radiation, powerful stellar flares, and unusual gravitational effects appeared likely to make these worlds uncomfortable places. Early discussions often focused more on the problems than the possibilities. As telescopes improved, however, the picture slowly became more interesting. Astronomers began discovering planet after planet orbiting red dwarfs. Some were rocky worlds similar in size to Earth. Others appeared to lie inside regions where temperatures could allow liquid water to exist on the surface. Suddenly, these once overlooked stars became some of the most exciting targets in astronomy. Instead of asking whether planets existed around red dwarfs, researchers began asking what those planets might actually be like. Imagine standing on one of these distant worlds. The star overhead would not resemble our bright sun. It might appear deeper orange or soft crimson, casting gentle light across mountains, oceans, and clouds. The daytime might seem dimmer than an overcast afternoon on Earth, yet bright enough for an entirely different kind of landscape. Shadows would stretch across unfamiliar terrain, while the surrounding sky might glow in colors no human has ever witnessed with their own eyes. Everything about such a planet could feel both strangely familiar and wonderfully different. Rivers might still carve valleys through rock. Rain could still fall from clouds. Winds might still shape coastlines over millions of years. Ice could still form near the poles. Volcanoes might still build towering mountains. The familiar laws of physics would continue operating. Yet every detail would be influenced by the quiet personality of the small red star at the center of the planetary system. Throughout this series, we will slowly explore these remarkable possibilities. We will examine how red dwarfs are formed, why they shine so gently, how planets circle them, whether oceans could survive beneath crimson sunlight, how atmospheres might protect living organisms, what strange plants could look like beneath reddish skies, whether animals might adapt to endless daylight or endless night, and how future telescopes may eventually discover unmistakable signs of life around these humble stars. Rather than focusing on spectacular explosions or violent cosmic disasters, this journey invites us to appreciate patience. The universe is often imagined as dramatic and chaotic, but red dwarfs remind us that some of its greatest stories unfold almost silently. Their light is faint, their pace is slow, and their lifetimes extend beyond ordinary imagination. In that quiet endurance may lie one of the greatest opportunities for life anywhere in the cosmos. Before we can wonder whether life might flourish around a red dwarf, it helps to become familiar with the star itself. The name may sound mysterious, almost as though it belongs to a distant legend. But a red dwarf is simply one of the smallest and coolest kinds of stars that nature can produce, while still allowing nuclear fusion to take place in its core. It is not a dying star, nor is it a failed star. It is a true star, quietly shining through the darkness with remarkable patience. Although its light is gentle, it is powered by the very same process that illuminates our own sun. Deep inside its center, hydrogen atoms slowly combine into helium, releasing energy that steadily travels outward before escaping into space as light and heat. If you could place a typical red dwarf beside our sun, the difference would be immediately obvious. The sun appears broad, brilliant, and intensely luminous. A red dwarf would look much smaller, perhaps only a fraction of its diameter. Some are little more than 1/10 the size of the sun, while others approach half its diameter. Their surfaces are cooler as well. Our sun has a surface temperature of nearly 5,500 degrees Celsius, while many red dwarfs remain between 2,400 and 3,700 degrees Celsius. Although these temperatures are still unimaginably hot by everyday standards, they are cool enough for the stars to glow with a soft reddish or orange appearance, rather than the bright yellow-white light we know so well. Their lower temperature explains why they appear so dim. Brightness depends not only on how hot a star is, but also on how large it is. A giant campfire gives off far more light than a single glowing ember, even though both contain burning material. In much the same way, a smaller, cooler star naturally produces far less light than a larger, hotter one. Some red dwarfs shine with less than 1,000th of the sun's brightness. If one of these stars replaced our sun while remaining at the same distance from Earth, daylight would nearly disappear. The sky would resemble a long twilight, and the warmth that supports our oceans and forests would quickly vanish. Yet these stars are anything but rare. In fact, if you could somehow count every star in the Milky Way, you would find that red dwarfs greatly outnumber stars like our sun. Imagine walking through a vast forest where 7 out of every 10 trees belong to the same species. Eventually, you would stop thinking of that species as unusual and instead recognize it as the ordinary background of the landscape. The Milky Way is much the same. The brilliant stars that attract our attention often represent only a small portion of what truly fills our galaxy. The quieter red dwarfs form its hidden foundation. Part of the reason they remained overlooked for so long is simply that they are difficult to see. Human eyes naturally notice bright objects. Ancient civilizations mapped the stars visible above them, creating constellations that still guide us today. Most red dwarfs are too faint to appear without telescopes. Even some of our closest stellar neighbors remained unknown until astronomers developed instruments sensitive enough to detect their dim glow. This means that the night sky we admire with our own eyes tells only part of the story. Behind many of the visible stars lies an even larger population of faint red suns quietly scattered throughout the galaxy. Their appearance would also surprise anyone fortunate enough to visit one. From a great distance, a red dwarf may seem like a tiny glowing ruby suspended in darkness. Up close, however, it would still be an immense sphere of intensely hot gas. Its surface would ripple with turbulent currents of glowing plasma. Towering arcs of magnetic energy could stretch high above the surface before falling back again. Darker regions, similar to the sun's sunspots, might slowly drift across its face. Although these stars appear calm from afar, they remain dynamic places where gravity, heat, and magnetism constantly interact. One of the most remarkable qualities of a red dwarf is how efficiently it uses its fuel. Larger stars consume hydrogen at astonishing rates, almost like enormous engines running at full power every moment. A red dwarf behaves more like a carefully managed lantern, releasing its energy slowly and steadily. This patient approach allows it to continue shining for periods so long that they exceed the current age of the universe many times over. It wastes very little of its precious hydrogen, mixing much of its interior so that fresh fuel gradually reaches the core. This slow rhythm becomes one of the defining characteristics of these stars, and one of the main reasons scientists consider them so intriguing when discussing the possibility of life. Despite their small size, red dwarfs possess enough gravity to hold entire planetary systems together. Rocky planets, icy worlds, and perhaps even gas giants may circle them in graceful orbits for billions upon billions of years. Because the star itself changes only very slowly, these planetary systems can remain remarkably stable over immense stretches of cosmic time. A mountain rising on one of those planets might erode into a plain, while the parent star appears almost unchanged. Oceans could form, continents could drift, and life, if it exists, might experience countless generations beneath a sky illuminated by the same quiet crimson sun. For scientists searching for life beyond Earth, this stability is both comforting and fascinating. A world needs more than the right ingredients. It also needs time. Chemistry must gradually become biology. Simple cells must slowly adapt to changing environments. Evolution requires countless opportunities, each building upon those that came before. A star that remains steady for unimaginable lengths of time provides an environment where such long processes might unfold without interruption. It is a reminder that in the universe, the brightest objects are not always the most important. Sometimes the quietest stars, almost invisible from afar, may offer the greatest opportunity for nature to patiently write its longest stories. Every red dwarf begins its story in darkness, long before it shines, long before planets circle around it, and long before any possibility of life can emerge nearby. It exists only as part of an enormous cloud of gas and dust, drifting almost silently through the galaxy. These clouds are unimaginably large, stretching across distances that would take light many years to cross. From afar, they appear peaceful, but within them, tiny changes are constantly taking place. Gravity slowly gathers scattered material together, creating denser regions that gradually become the seeds of future stars. These stellar nurseries are among the coldest places in space. Temperatures are so low that many gases move only sluggishly, allowing gravity to work with extraordinary patience. Nothing dramatic happens in a single moment. Instead, thousands of years pass, then hundreds of thousands, and eventually millions. The cloud contracts almost imperceptibly. As more material falls inward, the growing center becomes heavier, denser, and warmer. It is as though nature is carefully shaping a tiny ember deep inside an endless blanket of darkness. Eventually, the pressure becomes so great that the young object begins to glow faintly. At first, this light comes simply from the heat created by collapsing gas. It has not yet become a true star. It is often called a protostar, a star still in the process of forming. During this stage, it continues gathering material from the surrounding cloud, becoming slightly larger and hotter with each passing age. If enough mass accumulates, the temperature at its center rises to several million degrees. Under these extreme conditions, hydrogen atoms begin to merge into helium. The first sustained nuclear fusion has begun. At that quiet moment, a genuine star is born. The amount of material collected during formation determines nearly everything about the star's future. Massive stars gather enormous quantities of gas and become brilliant blue giants that blaze with extraordinary intensity. Smaller stars collect far less material. A red dwarf forms when the growing star never becomes particularly massive. It gathers only enough gas to ignite fusion while remaining among the lightest members of the stellar family. This modest beginning shapes every chapter that follows. Because a red dwarf contains less mass, gravity squeezes its core less forcefully than it does inside larger stars. The temperatures remain lower, and nuclear fusion proceeds at a much gentler pace. Imagine two candles burning side by side. One has a large flame that quickly consumes its wax. The other burns with a tiny, steady flame, using only a little fuel each hour. Long after the larger candle has disappeared, the smaller one continues glowing quietly. A red dwarf behaves much like that patient flame, conserving its fuel with remarkable efficiency. The sun, despite feeling wonderfully constant during a human lifetime, is actually consuming hundreds of millions of tons of hydrogen every second. This sounds astonishing, yet its enormous size allows it to continue for billions of years. Even so, astronomers know that one day the sun will exhaust the hydrogen in its core. Its appearance will change dramatically as it expands into a red giant before eventually settling into its final stages. Red dwarfs follow an entirely different rhythm. Their slower fusion allows them to preserve their hydrogen for periods so vast that ordinary numbers begin to lose their meaning. One reason for this extraordinary longevity lies hidden within the star's interior. In stars like the sun, much of the hydrogen remains trapped outside the central region where fusion occurs. Only the innermost portion is actively producing energy. A red dwarf behaves differently. The hot gas inside is constantly circulating, rather like water slowly moving through a gently heated pot. This movement mixes fresh hydrogen toward the center while carrying helium outward. As a result, a much larger fraction of the star's total hydrogen supply eventually becomes available for fusion, instead of using only a small reserve. The star gradually gains access to almost all of its fuel. This continuous mixing gives red dwarfs an astonishing level of efficiency. Very little hydrogen goes unused. Every portion of the interior contributes over immense spans of time. It is almost as though the star refuses to waste anything. Every atom has an opportunity to participate in the slow production of light. This remarkable economy allows these stars to shine steadily for hundreds of billions, and in many cases trillions, of years. To appreciate how extraordinary this is, it helps to compare these timescales with familiar history. Modern humans have existed for only a few 100,000 years. Agriculture appeared roughly 10,000 years ago. Written history covers only a few thousand years. The pyramids of Egypt are ancient by human standards, yet they were built only yesterday compared with the age of the Earth. Earth itself is about 4.5 billion years old. Already an almost unimaginable length of time. Yet many red dwarfs are expected to remain stable for hundreds of times longer still. Their future stretches far beyond anything our planet has yet experienced. Perhaps the most fascinating consequence is that the universe itself is still very young. From the perspective of these stars, every red dwarf that has ever formed is still alive today. None has yet reached the natural conclusion of its stellar life. because there simply has not been enough time since the birth of the cosmos. Astronomers can calculate how these stars are likely to evolve, but no one has ever observed an elderly red dwarf completing its life cycle. The universe has not existed long enough for such an event to occur. This realization changes the way we think about cosmic history. Many of the brightest stars that once illuminated the early universe have already disappeared. Some exploded as spectacular supernovae, scattering heavy elements across space. Others quietly transformed into compact stellar remnants. Meanwhile, countless humble red dwarfs continue shining almost exactly as they did billions of years ago. They have watched entire generations of stars appear and vanish while remaining nearly unchanged themselves. For any nearby planet, this enduring stability could be profoundly important. Imagine a world where the parent star changes so slowly that countless oceans may form. Continents shift, mountain ranges rise and wear away, and life evolves through endless generations beneath an almost unchanging sky. Evolution often depends not on speed but on consistency. A stable environment gives nature the opportunity to experiment patiently, allowing tiny changes to accumulate over immense stretches of time. The birth of a red dwarf may begin quietly within a cold cloud of gas, but its future becomes one of the longest-lasting stories the universe can tell. These modest stars are not remarkable because they shine brightly. They are remarkable because they endure. Their patient glow continues through ages that dwarf the history of planets, civilizations, and even galaxies, offering a calm and persistent source of light that may one day reveal worlds where life has had more time to grow than anywhere we have yet imagined. If you could stand aboard a spacecraft and slowly approach a red dwarf from the darkness of interstellar space, the first thing you might notice would not be overwhelming brilliance, but restraint. Unlike the dazzling light of larger stars, a red dwarf does not dominate its surroundings from great distances. It glows with quiet confidence, like a lantern shining across a calm valley on a peaceful evening. As the distance gradually closes, the star grows brighter, yet it never loses the gentle character that defines it. Its light is not weak because it is failing. It is gentle because that is simply the nature of the smallest true stars. Brightness can sometimes be misleading. Human eyes naturally associate brightness with importance. We notice fireworks more easily than candlelight, lightning more readily than the steady glow of the moon. Yet, in the universe, brilliance is only one way a star can exist. A red dwarf reminds us that power can also be expressed through patience. Instead of releasing enormous amounts of energy in a short lifetime, it stretches its energy across spans of time so vast that entire chapters of cosmic history unfold beneath its constant glow. The color of a red dwarf is another feature that deserves careful attention. Despite the name, many red dwarfs would not appear vividly red to human eyes if viewed from nearby. Some would seem deep orange, others copper-colored, while many would have a warm reddish-orange appearance similar to glowing charcoal or the last moments of a sunset. The exact shade depends largely on the star's surface temperature. Slightly warmer red dwarfs produce more orange light, while cooler ones shift further toward red. None resemble a bright crimson lamp. Instead, they radiate subtle colors that feel calm rather than dramatic. This color comes from the temperature of the star's outer layers. Every object that is heated emits light, and the hotter it becomes, the bluer that light gradually shifts. Cooler objects radiate more energy at longer wavelengths. Because red dwarfs have cooler surfaces than stars like our sun, much of their energy is emitted in deep red and infrared wavelengths. Infrared light lies just beyond what human eyes can detect. Although invisible to us, it carries warmth and energy that instruments can easily measure. If a person somehow visited a planet orbiting one of these stars, their eyes might perceive a world unlike anything on Earth. The daylight could feel softer, almost as though the sun were permanently filtered through a gentle evening haze. Shadows would still exist, but they might not appear as sharp. Bright blue skies, so familiar on Earth, could give way to skies with different tones depending on the planet's atmosphere. Sunsets might blend gradually into the surrounding daylight, instead of producing the brilliant explosions of color we often enjoy on our own world. The plants, rocks, clouds, and oceans of such a planet would all reflect this unusual light in different ways. A forest growing beneath a red dwarf might not appear green from a human perspective. Leaves could evolve darker pigments that absorb more of the available light, perhaps appearing almost black, deep purple, or rich burgundy. These colors would not necessarily be signs of decay. Instead, they could represent highly efficient ways of gathering the limited energy provided by the parent star. Nature on Earth has already demonstrated extraordinary flexibility, producing plants with leaves that range from bright green to nearly black under certain conditions. On another world, evolution might take this creativity even further. Even ordinary landscapes would carry a different atmosphere. Snow might reflect the reddish sunlight with a faint pink glow. Desert sands could shimmer with copper-colored highlights. Oceans might mirror a crimson sky during calm weather, creating horizons unlike any seen on Earth. The familiar relationship between light and color would remain governed by the same physical laws, yet the results would feel beautifully unfamiliar. One fascinating characteristic of red dwarfs is that their dimness requires nearby planets to orbit much closer than Earth orbits the Sun. Although the star itself is faint, distance changes everything. Sitting close to a campfire can feel comfortably warm even when the flames are small. The same principle applies in space. A planet orbiting very near a red dwarf may receive nearly as much total energy as Earth receives from the Sun. To anyone standing on its surface, the star could even appear surprisingly large in the sky because of that close proximity, despite its much smaller physical size. Imagine looking upward each morning to see a reddish-orange sun that occupies more of the sky than our own sun does from Earth. It would not shine with blinding intensity, yet its broad disk would become a constant reminder of how closely your world circles its parent star. Days would begin beneath its gentle glow, and evenings would fade beneath the same warm light, without ever reaching the brilliant white brightness familiar to us. The gentle nature of a red dwarf also affects the rhythm of its planetary system. Because these stars change very slowly over billions of years, the amount of energy reaching nearby planets remains remarkably steady for immense periods. On Earth, the sun's brightness has increased gradually throughout geological history, influencing climate over billions of years. A red dwarf evolves much more slowly. Its light remains comparatively stable across intervals that seem almost endless. This stability provides an unusually consistent environment where oceans, atmospheres, and perhaps living organisms have the opportunity to adapt over extraordinary lengths of time. Yet gentle does not always mean simple. Beneath the peaceful appearance of many red dwarfs lies a surprisingly active magnetic personality. Their surfaces can occasionally unleash powerful bursts of energy that temporarily transform the calm star into something far more energetic. During these moments, radiation pours into surrounding space, reminding astronomers that even the quietest stars possess hidden forces. These sudden events have become one of the central questions in the search for life around red dwarfs. Can nearby planets remain safe beneath such an unpredictable sky? Or can atmospheres and magnetic fields soften the effects of these stellar outbursts enough for life to endure? For now, it is enough to appreciate the quiet beauty of the stars themselves. They may never dominate the heavens with dazzling brilliance, but they offer something equally remarkable. Their soft crimson light, their extraordinary patience, and their unwavering endurance create a kind of cosmic calm that is rare among the more dramatic members of the stellar family. In a galaxy filled with brilliant giants that live fast and disappear young, the smallest stars choose another path. They shine gently, they change slowly, and they continue illuminating the darkness long after brighter stars have faded into memory. One of the first questions people ask when thinking about life beyond Earth is wonderfully simple. Is the planet too hot, too cold, or just warm enough for liquid water to exist? This idea has guided astronomers for decades because, on our own world, every known living organism depends on liquid water in one way or another. Oceans shape climates, rivers carry nutrients, rainfall supports forests, and even the smallest microscopic cells rely on water to carry out the chemistry of life. Before we imagine strange plants beneath crimson skies or unfamiliar animals wandering across distant continents, we first have to ask whether water could remain in its liquid form for millions or even billions of years. Around every star, there exists a region where temperatures may allow this possibility. Astronomers often call it the habitable zone. Despite its impressive name, it is not a guarantee that life exists there. It simply marks the range of distances where the overall amount of heat reaching a planet could allow liquid water to remain on its surface, provided the planet also has an atmosphere with suitable pressure. Think of it as a neighborhood rather than a destination. A comfortable neighborhood offers the potential for a pleasant home, but the house itself still needs strong walls, clean water, and many other important qualities. Our own Earth happens to orbit comfortably within the Sun's habitable zone. Venus circles a little closer and has become extraordinarily hot, with thick clouds trapping heat until its surface reaches temperatures capable of melting lead. Mars travels farther away and today is mostly cold and dry, although evidence suggests that rivers and lakes once existed there long ago. Earth lies between these extremes, receiving just enough sunlight to maintain vast oceans that have endured for billions of years. This fortunate position has allowed life to flourish across almost every corner of the planet. A red dwarf changes this familiar picture in an interesting way. Because it shines much less brightly than the sun, its habitable zone lies far closer to the star. Instead of orbiting at roughly 150 million kilometers as Earth does, a potentially habitable planet around a red dwarf may circle only a few million kilometers away. On a map of our own solar system, such an orbit might fit well inside the path traveled by Mercury. What would seem impossibly close to the sun can be perfectly comfortable around a much dimmer red dwarf. This close relationship creates a sky that would feel very different from our own. The parent star would appear much larger than the sun appears from Earth, simply because the planet is so near. Sunrise might reveal a broad reddish disk, slowly climbing above distant mountains, or emerging over a quiet ocean. Even though the star itself is smaller, its closeness allows it to dominate the sky. It would become a constant presence, reminding every living thing that the source of warmth lies only a short distance away in cosmic terms. Distance also affects the rhythm of the planet's year. Because these worlds orbit so closely, they complete one trip around their star much more quickly than Earth completes its journey around the sun. While our year lasts about 365 days, some planets within the habitable zones of red dwarfs finish an entire orbit in only a few weeks. Imagine celebrating a birthday every month. Entire calendars would be built around completely different ideas of time. Seasons, if they existed at all, might follow patterns unlike anything familiar to us. The habitable zone itself is not a sharp boundary. There is no invisible line where one step inward suddenly boils every ocean, while one step outward instantly freezes every sea. Instead, it is a gradual transition. Conditions depend on many factors beyond simple distance. The thickness of the atmosphere, the amount of cloud cover, the reflectivity of ice, the presence of oceans, volcanic activity, and even the types of gases surrounding the planet all influence its average temperature. Two planets orbiting at nearly the same distance from the same star may experience remarkably different climates. Earth demonstrates this beautifully. Our atmosphere contains gases that naturally trap part of the sun's warmth. Without this greenhouse effect, Earth's average temperature would fall well below the freezing point of water. Oceans would become vast sheets of ice, and the rich diversity of life we know today would never have appeared. A similar process could occur on planets orbiting red dwarfs. Even if they receive only modest amounts of stellar energy, a suitable atmosphere could preserve enough warmth to maintain rivers, lakes, and oceans for extraordinary periods of time. Clouds also become important partners in shaping climate. Thick cloud layers can reflect incoming light back into space, cooling the planet beneath them. At the same time, clouds can trap heat rising from the surface, especially during long nights. The balance between these opposing effects determines whether the overall climate remains mild or gradually shifts toward freezing or overheating. Scientists use complex computer models to explore thousands of possible combinations, discovering that some red dwarf planets may possess surprisingly stable climates, despite orbiting so close to their stars. Oceans contribute another layer of stability. Water stores heat remarkably well. During warmer periods, it absorbs excess energy, and during cooler periods, it slowly releases that stored warmth back into the atmosphere. On Earth, this gentle exchange softens temperature differences between day and night, and between different seasons. A distant planet with large oceans could experience a similar moderation, helping maintain environments where life has the opportunity to adapt gradually rather than facing constant extremes. The possibility of underground water also expands the picture. Even if surface conditions become cold in certain regions, geothermal heat rising from the planet's interior may keep water liquid beneath layers of ice. On Earth, hidden lakes exist beneath Antarctica's thick ice sheets, isolated from the surface for immense periods. Deep beneath the oceans, hydrothermal vents support thriving ecosystems entirely independent of sunlight. These examples remind us that life can find surprising refuges even when surface conditions appear challenging. As astronomers continue discovering new planets around nearby red dwarfs, many of them fall within these carefully calculated habitable zones. Each discovery adds another candidate to the growing list of places where liquid water might exist. Some worlds are slightly larger than Earth, while others are nearly identical in size. Their exact conditions remain uncertain because they are simply too distant to observe directly in great detail. Yet every new detection quietly expands our imagination, suggesting that the galaxy may contain far more potentially comfortable worlds than anyone once believed. The habitable zone is therefore not a promise, but an invitation. It tells us where nature may have arranged the first important ingredient for life, but countless other pieces of the puzzle remain to be explored. The gentle warmth of a red dwarf, combined with the right distance, a protective atmosphere, flowing water, and enough time, could transform an ordinary rocky planet into a living world where rivers carve valleys beneath a crimson sun, clouds drift across unfamiliar skies, and life patiently writes its story over billions of quiet years. A planet may orbit within the habitable zone of a red dwarf and still face an important question. Can it actually keep its water for billions of years? This may sound like a simple problem, but in reality, it is one of the greatest mysteries in planetary science. Water is surprisingly resilient, yet it is also surprisingly fragile. It can freeze into enormous glaciers, flow as rivers across continents, gather into deep oceans, or disappear into the atmosphere as invisible vapor. Over immense stretches of time, entire seas can be lost to space or locked away beneath rock and ice. Whether a distant world remains blue and full of oceans depends on a delicate balance between the planet itself and the quiet star it circles. On Earth, water is constantly moving through an endless cycle. Rain falls from clouds onto forests, mountains, and open fields. Streams gather into rivers that eventually reach the sea. Sunlight warms the oceans, allowing water to evaporate back into the atmosphere, where it forms clouds once again. This process has continued for hundreds of millions of years with remarkable consistency. It shapes landscapes, regulates temperatures, and provides every known ecosystem with one of its most essential ingredients. Looking at Earth from space, the brilliant blue oceans immediately reveal how important water has become in the story of our planet. A young rocky planet forming around a red dwarf may begin with a generous supply of water. Some of it arrives trapped inside minerals that formed during the planet's creation. Some may be delivered later by icy asteroids and comets wandering through the young planetary system. During the early stages of formation, countless impacts scatter material across space, mixing ice, rock, and metals into growing worlds. The exact amount of water each planet receives can vary enormously. One world may develop oceans covering much of its surface, while another may end up with only scattered lakes or hidden underground reservoirs. Gravity plays an important role in keeping that water from escaping. A larger planet usually has stronger gravity, making it more difficult for water molecules and atmospheric gases to drift into space. Smaller worlds face a greater challenge. Over billions of years, their lighter gravity allows some gases to gradually leak away. Mars provides a familiar example. Although rivers once flowed across its surface, much of its atmosphere eventually disappeared, leaving behind the cold, dry landscape we see today. This reminds us that simply having water at the beginning does not guarantee that it will remain. The atmosphere acts as a protective blanket. It not only traps warmth, but also shields the surface from many harmful influences. If the atmosphere remains thick enough, liquid water can survive over a wide range of conditions. Atmospheric pressure determines whether water stays liquid, freezes into ice, or immediately evaporates. At Earth's surface, pressure allows lakes and oceans to remain stable across most climates. Without sufficient pressure, even comfortable temperatures may fail to support liquid water. Red dwarf planets introduce another interesting possibility. Because they orbit close to their stars, many receive nearly constant levels of energy. If the atmosphere distributes this heat effectively, oceans may remain stable over enormous periods. Winds could carry warm air toward cooler regions, while ocean currents slowly transport heat around the globe. On Earth, these currents help prevent extreme temperature differences between different parts of the planet. A similar process could operate on distant worlds, creating climates far more balanced than their unusual orbits might first suggest. Water itself becomes one of the planet's greatest climate stabilizers. It absorbs heat slowly during warmer periods and releases it gradually as temperatures fall. Large oceans therefore act like enormous thermal reservoirs. Imagine placing a stone and a bucket of water beneath the afternoon sun. The stone becomes hot very quickly, while the water warms much more slowly. Long after sunset, however, the water continues releasing its stored heat while the stone cools rapidly. Entire oceans perform the same quiet service for planetary climates, smoothing out changes that might otherwise become severe. Clouds add another layer of protection. Thick cloud systems reflect part of the incoming light back into space, preventing excessive warming. At the same time, they reduce heat loss from the surface below. Depending on their height, thickness, and composition, clouds can either cool or warm a planet. On a world orbiting a red dwarf, persistent cloud formations near the point directly beneath the star could even help prevent overheating by reflecting a portion of the constant sunlight away before it reaches the ground. Not all water must remain on the surface. Some may seep deep underground, filling vast networks of cracks within ancient rocks. On Earth, groundwater stores enormous quantities of fresh water hidden beneath our feet. Entire underground rivers flow silently through caves for hundreds of kilometers. Similar systems could exist beneath the surface of red dwarf planets. Even if surface conditions became temporarily difficult, underground reservoirs might preserve liquid water where temperatures remain remarkably stable. Volcanic activity also contributes to the long-term survival of water. Volcanoes release water vapor, carbon dioxide, and many other gases trapped within the planet's interior. These gases gradually replenish the atmosphere over geological time. Earth's volcanoes have quietly participated in this recycling process for billions of years, helping maintain the atmosphere that protects life today. A distant rocky world with active volcanoes could experience similar renewal, replacing gases that are slowly lost to space and supporting a climate capable of sustaining liquid water. Ice should not be viewed as the opposite of habitability. Frozen water often serves as an important reserve waiting for warmer conditions. Earth's polar ice sheets contain astonishing quantities of fresh water. During different periods of Earth's history, glaciers expanded and retreated many times without ending the story of life. On another planet, seasonal or permanent ice could exist alongside warm oceans, creating beautiful contrasts between frozen landscapes and temperate regions. Life, if present, might adapt to both environments with remarkable flexibility. Scientists studying exoplanets often remind themselves that water can exist in many forms beyond the familiar image of blue oceans beneath sunny skies. It may hide beneath kilometers of ice, fill underground caverns, collect in shallow inland seas, or circulate through dense atmospheres before returning as gentle rain. Every possibility broadens our understanding of where life might find a foothold. The greatest uncertainty comes during the earliest years of a red dwarf's life. Young red dwarfs are often much more active than they become later, releasing stronger bursts of radiation and energetic particles. If a newly formed planet cannot protect its atmosphere during this turbulent youth, significant amounts of water may gradually be lost. On the other hand, if the atmosphere is sufficiently thick, if the planet possesses a strong magnetic field, or if additional water continues arriving from icy bodies, much of that precious resource may survive the difficult beginning. Once the star settles into its long, steady adulthood, conditions may remain surprisingly calm for hundreds of billions of years. When we imagine life around a red dwarf, it is easy to picture endless oceans glowing beneath a crimson sky. Reality is likely to be far more varied. Some worlds may indeed become ocean planets, where water stretches uninterrupted from horizon to horizon. Others may resemble Earth, with continents, islands, winding rivers, and deep inland lakes. Still others could hide most of their water beneath the surface, waiting patiently beneath layers of ancient rock. Each possibility reminds us that water is not merely a feature of a planet. It is part of a living system, constantly moving, constantly changing, and quietly shaping the environments where life may one day emerge and endure. As astronomers began discovering planets around red dwarfs, one particular phrase appeared again and again in scientific discussions: tidal locking. At first, the term sounds technical, perhaps even intimidating, but the idea behind it is surprisingly easy to picture. It is a natural consequence of gravity, time, and distance. In fact, we already have an example much closer to home. Every time you look up at the moon, you are seeing the result of tidal locking in action. The moon always shows Earth the same face. The familiar patterns of dark volcanic plains and bright highlands have greeted every generation of human observers for thousands of years. Meanwhile, the opposite side remained completely unknown until spacecraft finally traveled around it. This happens because the moon rotates on its axis at exactly the same rate that it orbits Earth. One complete rotation takes the same amount of time as one complete orbit. As a result, the same hemisphere continually faces our planet. This is not a strange coincidence. It is the quiet work of gravity over immense stretches of time. Long ago, the young moon probably rotated much more quickly. Earth's gravity gently pulled on it, creating tiny distortions within its rocky interior. Those distortions generated heat, gradually slowing the moon's rotation until it reached a stable balance. Once that balance was achieved, the moon settled into the familiar pattern we observe today. A similar process may affect many planets orbiting red dwarfs. Because these worlds travel extremely close to their stars, The star's gravity has a much stronger influence than the sun's gravity has on Earth. Over millions or billions of years, that constant gravitational pull can gradually slow a planet's rotation until it too becomes tidally locked. Instead of experiencing an ordinary cycle of sunrise and sunset every 24 hours, one side of the planet would always face the star while the opposite side would remain turned away. At first glance, this sounds like a place where life could never survive. It is easy to imagine one hemisphere burning beneath endless daylight while the other freezes beneath eternal darkness. For many years, this picture shaped the public imagination. Artists often painted tidally locked planets as worlds divided sharply between fire and ice, with no comfortable regions in between. It was an elegant image, but nature often proves to be more subtle than our first impressions. Modern climate simulations suggest that the story may be far more hopeful. A planet with a sufficiently thick atmosphere does not allow heat to remain trapped on one side forever. Warm air naturally rises in the illuminated hemisphere and begins flowing toward cooler regions. As it moves, it carries energy with it. Cooler air then returns toward the day side near the surface, creating enormous global wind patterns that slowly distribute warmth around the planet. Earth already demonstrates this principle every day. The equator receives far more solar energy than the polar regions. Yet the poles are not as cold as they would be if the atmosphere and oceans remained completely still. Winds transport heat across continents, while ocean currents quietly carry warm water toward higher latitudes. Without these natural circulation systems, the differences between tropical and polar climates would be dramatically greater. On a tidally locked planet, these atmospheric movements could become even more impressive. Instead of following familiar daily heating and cooling cycles, the atmosphere would respond to one permanent source of warmth. Giant circulation cells might extend across entire hemispheres. Powerful jet streams could continuously move between the bright and dark sides of the world, creating weather systems unlike anything on Earth while still maintaining a surprisingly stable overall climate. Oceans would strengthen this balancing act. Water absorbs heat during its long exposure to the day side and slowly transports that energy through currents toward the night side. There, it gradually releases its stored warmth into the colder atmosphere before returning once again. Over millions of years, these immense planetary currents could become as steady as the heartbeat of the planet itself, quietly preventing the permanent freezing that early scientists once feared. The point directly beneath the star would receive the greatest amount of light. If you stood there, the star would appear fixed in the sky, never rising and never setting. Time would still pass, clouds would still drift overhead, rain might still fall, and seasons could still occur if the planet's orbit were slightly elliptical or its axis modestly tilted. Yet the star itself would remain suspended in nearly the same position day after day, century after century. It would become a permanent feature of the landscape, as constant as a mountain on the horizon. Far away, on the opposite hemisphere, the experience would be entirely different. There, the star would never appear above the horizon. The sky would remain permanently dark, illuminated only by distant stars, glowing nebulae, and perhaps the soft light reflected from nearby moons. Temperatures would certainly be lower than on the day side, but whether they reached extreme levels would depend greatly on the atmosphere's ability to transport heat. If enough warmth arrived through winds and ocean currents, even the night side might avoid becoming a frozen wasteland. Between these two extremes lies one of the most fascinating regions imagined by planetary scientists. Around the edge, separating endless day from endless night, could exist a broad band of perpetual twilight. Here, the star would remain forever near the horizon, casting long golden or reddish shadows across the landscape. The light would never become fully bright, yet darkness would never completely arrive. Gentle sunsets would stretch endlessly across the sky without ever reaching their conclusion. This twilight region has captured the imagination of scientists and artists alike because it may offer some of the most comfortable conditions on a tidally locked planet. Temperatures could remain moderate, neither excessively hot nor bitterly cold. Rivers might flow toward darker regions where they gradually freeze, while warmer currents return beneath the surface. Clouds could gather where warm and cool air continuously meet, creating belts of frequent rainfall that nourish vast ecosystems. Plants, if they evolved there, might adapt to the constant angle of the incoming light. Trees would never experience changing daylight lengths. Flowers would not wait for sunrise. Animals would not measure time by dawn and dusk as many species do on Earth. Instead, entirely different biological rhythms might emerge. Life could organize itself around weather patterns, temperature cycles, tides, or seasonal variations, rather than the familiar alternation of day and night. Even human visitors would likely need time to adjust. Without a rising and setting sun, our natural sense of time would gradually lose one of its oldest guides. Clocks would still function, of course, but the landscape itself would provide few visual reminders that another day had begun. The steady crimson glow on the horizon could make every hour feel connected to the next in one long, peaceful continuum. Tidal locking was once considered one of the greatest obstacles to life around red dwarfs. Today, it is viewed with greater curiosity than fear. While it certainly creates environments unlike anything found on Earth, research increasingly suggests that these worlds may remain surprisingly livable under the right conditions. Rather than dividing a planet into impossible extremes, gravity may quietly create landscapes where winds, oceans, clouds, and life itself learn to adapt to a sky that never changes its face. Imagine standing on a planet where the sky never changes in the way we know it on Earth. There is no sunrise slowly brightening the horizon, no afternoon drifting toward evening, and no sunset marking the end of the day. Instead, the sky remains almost exactly the same throughout your entire lifetime. The position of the star hardly changes. The landscape is illuminated by a steady crimson glow that has remained constant for millions of years. At first, this may seem strange, but after enough time it would simply become normal. Every creature born on such a world would grow up believing that this unchanging sky was the natural order of the universe. A tidally locked planet can be imagined as three enormous regions that gradually blend into one another. The first is the permanent day side, where the red dwarf always hangs overhead. The second is the permanent night side, where the star never appears at all. Between them lies a broad transition zone, often called the twilight belt, a region that may prove to be one of the most comfortable environments on the entire planet. The day side receives a constant stream of energy from the nearby star. Since the sunlight never disappears, the ground has endless opportunities to warm. Rocks slowly absorb heat. Oceans collect energy hour after hour. Warm air rises continuously, beginning long atmospheric journeys toward cooler parts of the world. Yet this does not necessarily mean the day side becomes unbearably hot. If thick clouds develop directly beneath the star, they can reflect a significant amount of incoming light back into space. This natural mirror may prevent temperatures from climbing to dangerous levels. Scientists using computer simulations have found that such cloud formations are not only possible, but may actually be expected. As warm air rises from the constantly illuminated surface, it cools at higher altitudes, allowing water vapor to condense into large cloud systems. These clouds could remain remarkably stable because the heating pattern never changes. Unlike Earth, where cloud systems constantly move with the changing position of the sun, a tidally locked world may maintain persistent cloud cover above its brightest regions for incredibly long periods. Beneath these clouds, life might experience a surprisingly gentle environment. Soft reddish daylight would filter through layers of vapor, producing an atmosphere similar to an endless calm afternoon. Rain could fall regularly, feeding rivers that slowly carve valleys across ancient landscapes. Lakes would fill and overflow. Waterfalls would tumble over cliffs that have stood beneath the same sky for hundreds of millions of years. The absence of sunrise and sunset would not prevent weather from shaping the land. Nature would simply follow a different rhythm. As one travels farther from the center of the day side, the star gradually appears lower in the sky. Shadows become longer. The light softens. Temperatures slowly begin to fall. This transition is so gradual that a traveler might walk for weeks before noticing meaningful changes. There is no sharp boundary where daylight suddenly ends. Instead, the world slowly shifts from bright crimson illumination into the endless glow of twilight. The twilight belt is perhaps the most captivating region on the planet. Here, the star remains forever near the horizon, never climbing high above it and never disappearing below it. Imagine an eternal sunrise or an endless sunset stretched across every day of every year. The landscape is bathed in warm orange and red tones that gently illuminate mountains, forests, rivers, and open plains. Long shadows become permanent features of the scenery, giving the land a peaceful appearance that never changes. Temperatures within this belt may remain remarkably comfortable. Warm air arriving from the dayside mixes with cooler air flowing from the nightside, creating moderate conditions that are neither excessively hot nor bitterly cold. Rainfall may also become more common here as moist air cools and condenses. Some scientists believe that if complex life exists on a tidally locked world, much of it could thrive within this broad region where energy, water, and temperature achieve a delicate balance. Imagine vast forests growing beneath an eternal horizon where the reddish sun never moves. Trees would not lean toward a changing source of light because the direction of illumination remains constant. Over countless generations, they might grow in unusual shapes, their branches spreading permanently toward the horizon instead of upward. Flowers would never need to open each morning or close each evening. Their biological clocks would evolve according to different signals, perhaps responding to subtle changes in humidity, temperature, or seasonal shifts rather than the familiar cycle of day and night. Animals would adapt as well. On Earth, many creatures measure time using sunlight. Birds begin singing before dawn. Owls emerge after sunset. Countless insects synchronize their behavior with the daily rhythm of light and darkness. On a tidally locked planet, those familiar schedules would have little meaning. Instead, life might organize itself around weather patterns, food availability, or internal biological cycles that continue independently of the sky. Activity and rest would still occur, but not because the sun had risen or set. Continuing farther toward the night side, the crimson glow slowly fades. The star slips lower until only a faint reddish light lingers along the horizon. Eventually, even that disappears, leaving behind a sky filled with countless stars. The darkness here would be profound, yet not necessarily lifeless. Heat carried by winds and oceans may prevent temperatures from falling to unimaginable extremes. Beneath the surface, geothermal energy continues rising from the planet's interior, warming underground caves, deep lakes, and networks of flowing groundwater. The night side could become a place of extraordinary beauty. Without the bright glare of a nearby sun, the Milky Way would stretch overhead with breathtaking clarity. Distant galaxies, colorful nebulae, and star clusters invisible from Earth's cities might dominate the heavens every moment of every year. If the planet possessed moons, they could wander slowly across the sky, reflecting the reddish light of the hidden star. Their gentle glow might provide enough illumination for landscapes of ice, rock, or quiet forests to emerge from the darkness. Ice may indeed become common in these colder regions. Vast glaciers could slowly advance across valleys before melting again as warm air occasionally reaches them. Frozen lakes might conceal liquid water beneath thick layers of ice, much as some of Earth's polar lakes do today. If oceans extend into the night side, currents carrying warm water from the day side could keep portions of them free from ice, creating ribbons of open sea surrounded by frozen coastlines. The boundary between light and darkness would never remain perfectly still. Weather constantly reshapes it. Clouds drift across the horizon. Storms carry moisture from one hemisphere to the other. Winds rise and weaken. Snow falls, melts, and falls again. The planet remains alive with movement, even though the star itself appears motionless. For someone visiting this world, traveling from the brightest regions to the deepest darkness would feel less like moving through time and more like moving through different climates on a single enormous continent. The journey would reveal deserts warmed by constant light, fertile twilight valleys rich with rivers and forests, and peaceful frozen landscapes beneath skies crowded with stars. Each region would possess its own beauty, its own challenges, and perhaps its own forms of life. Far from making such planets monotonous, tidal locking may create one of the most varied environments imaginable. Instead of repeating the familiar rhythm of morning and evening, the entire world becomes a continuous tapestry of climates arranged across its surface. Every step across the landscape brings subtle changes in light, temperature, and weather, offering nature countless opportunities to adapt and flourish beneath the quiet, unwavering glow of a small red star. Until now, the small red dwarf has seemed like one of the calmest objects in the universe. It shines slowly, uses its fuel carefully, and remains stable for unimaginably long stretches of time. It would be easy to imagine these stars as peaceful cosmic lanterns that never disturb the worlds surrounding them. In many ways, this picture is true, yet beneath their gentle appearance lies another side of their personality. One that occasionally reminds astronomers that even the quietest stars possess tremendous energy. Every star is made of plasma, a state of matter so hot that electrons are no longer permanently attached to atoms. This glowing plasma is constantly moving. It rises, cools, sinks, and rises again in enormous circulating currents. As it moves, it also carries magnetic fields with it. These invisible magnetic fields twist, stretch, and sometimes become tangled in remarkably complicated ways. Most of the time, this activity remains hidden beneath the calm appearance of the star, but occasionally the tension becomes too great. When that happens, the magnetic field suddenly rearranges itself. In only a few moments, an enormous amount of stored energy is released into space. Astronomers call this event a stellar flare. It is somewhat similar to stretching a rubber band farther and farther until it suddenly snaps back into place. The release is quick, dramatic, and surprisingly powerful. Our own sun produces solar flares quite regularly. Some are relatively small, while others are energetic enough to interfere with satellites, radio communications, and electrical systems here on Earth. During particularly strong solar storms, beautiful curtains of green, purple, and red light spread across polar skies as charged particles interact with Earth's atmosphere. These shimmering displays, known as the aurora, remind us that even our familiar sun occasionally becomes more active. Red dwarfs can produce similar flares, but in many cases, they are even more energetic compared with the overall size of the star. Because red dwarfs are smaller, their powerful magnetic fields can store enormous amounts of energy relative to their mass. Some flares briefly increase the brightness of the entire star by several times before fading again. For a planet orbiting nearby, such an event could dramatically change the environment for several hours, or even longer. Imagine standing beneath the steady crimson sky of a tidally locked world for countless days, weeks, or even years. The light has remained almost perfectly constant. Then, without warning, the star suddenly brightens. The reddish glow becomes noticeably stronger. The sky takes on a sharper brilliance, Invisible radiation pours outward through space, while streams of charged particles race away from the star at extraordinary speeds. To human eyes, the change might seem modest, but the invisible effects could be far more significant. Fortunately, distance alone does not determine whether a flare becomes dangerous. A planet's atmosphere serves as the first line of defense. Earth's atmosphere quietly protects every living creature from enormous amounts of ultraviolet radiation arriving from the sun each day. Without this protective layer, life on land would face a far harsher environment. The atmosphere absorbs much of the harmful radiation before it ever reaches the surface, allowing forests, oceans, animals, and people to thrive. A magnetic field provides another remarkable shield. Deep inside Earth, flowing liquid iron generates an enormous magnetic field that stretches far into space. This invisible barrier deflects many charged particles before they can reach the atmosphere. When some particles do slip through near the poles, they create the spectacular auroras that dance across northern and southern skies. A rocky planet orbiting a red dwarf could possess a similar magnetic shield if its interior remains active. Although invisible, this protective field might play one of the most important roles in preserving both the atmosphere and any life living beneath it. Charged particles arriving from the parent star would be guided around much of the planet rather than striking it directly over billions of years. This quiet protection could make the difference between a world that remains habitable and one that gradually loses its atmosphere to space. The age of the red dwarf also matters greatly. Young red dwarfs are often energetic and unpredictable. During their youth, they may produce frequent powerful flares as their magnetic fields remain especially active. This early period can last for hundreds of millions of years, far longer than many people might expect. For any nearby planet, these early ages represent an important test. If the atmosphere survives this active youth, the future may become considerably calmer. As red dwarfs grow older, many gradually settle into more stable patterns. Their rotation slows, magnetic activity often decreases, and the frequency of the strongest flares becomes lower. The star does not become completely quiet, but its behavior often becomes more predictable, since these stars can then remain stable for hundreds of billions or even trillions of years. An early period of turbulence may eventually give way to an unimaginably long era of relative calm. Scientists have discovered that not every red dwarf behaves in exactly the same way. Some remain highly active throughout much of their lives, while others become noticeably quieter as they age. This diversity means that every planetary system must be studied individually. Two planets orbiting stars of similar size may experience very different histories depending on the personality of their parent stars. Weather on such planets would not be shaped only by winds and clouds. Space itself would become part of the climate. Just as Earth experiences changing atmospheric weather, planets around red dwarfs may experience changing space weather. Most days could pass peacefully beneath steady crimson light, while occasional stellar outbursts briefly disturb the upper atmosphere. If intelligent life evolved there, it might learn to predict these stellar storms just as we forecast hurricanes or thunderstorms. Perhaps civilizations living beneath red dwarfs would construct observatories dedicated entirely to monitoring their quiet little sun. They might watch subtle changes on its surface, searching for signs that a flare is about to occur. Spacecraft could temporarily suspend sensitive operations. People might spend more time indoors while the strongest radiation passes. Afterward, life would continue almost exactly as before, beneath the familiar reddish sky. If the atmosphere were thick enough and the magnetic field sufficiently strong, many inhabitants might never even notice most flares. The invisible shields surrounding their world would quietly absorb the disturbance while rivers continued flowing, forests continued growing, and gentle rain continued falling. Only the most sensitive scientific instruments would reveal the invisible storm passing overhead. This possibility reminds us of an important lesson about habitability. A planet is never shaped by only one factor. A nearby orbit may increase exposure to stellar activity, but a protective atmosphere, a powerful magnetic field, deep oceans, and billions of years of gradual adaptation may together create an environment where life not only survives, but flourishes. Nature rarely depends on a single condition. Instead, countless systems work together, each quietly supporting the others. The occasional flare does not erase the remarkable advantages offered by red dwarfs. Their extraordinary lifespans still provide vast opportunities for evolution. Their abundance still means that countless rocky planets likely circle them throughout the galaxy. Their gentle everyday light still offers steady warmth to nearby worlds. The challenge lies in understanding how planets respond to the moments when that gentle star briefly reveals the immense energy hidden beneath its calm and patient surface. If there is one invisible feature that quietly determines the destiny of a planet, it is its atmosphere. From space, an atmosphere often appears as nothing more than a thin blue or golden line surrounding a distant world. Compared with the planet beneath it, the layer seems almost unbelievably delicate. Yet, within that fragile shell exists the difference between frozen silence and flowing rivers, between barren rock and thriving forests, between a lifeless landscape and one where countless forms of life can breathe, grow, and evolve. Earth provides a remarkable example of just how important an atmosphere can be. If someone could somehow remove every molecule of air surrounding our planet in a single instant, the transformation would be immediate and dramatic. The sky would become black even during midday. Sound would disappear because there would be no air to carry it. Liquid water exposed at the surface would begin behaving very differently under the sudden change in pressure. Temperatures would swing wildly between intense daytime heating and bitter nighttime cold. Every familiar ecosystem would collapse, yet the planet itself would remain almost unchanged in size. It is the invisible layers surrounding it that makes Earth feel alive. When astronomers search for potentially habitable planets around red dwarfs, one of their greatest questions is not simply whether those planets exist, but whether they have managed to keep their atmospheres across billions of years. A rocky world may possess oceans, mountains, and continents, but without a stable atmosphere, maintaining comfortable conditions becomes enormously difficult. The earliest years are often the greatest challenge. Young red dwarfs can be much more active than they become later in life. Powerful flares, energetic radiation, and streams of charged particles continually flow outward into surrounding space. Planets orbiting nearby receive the full attention of this youthful activity. Over millions of years, these energetic events may gradually strip away parts of an atmosphere, particularly if the planet lacks a strong magnetic field. Fortunately, losing an atmosphere is rarely a simple or immediate process. A planet is not a balloon that suddenly bursts. Instead, the atmosphere is constantly changing, being replenished, reshaped, and recycled through many natural processes. Volcanoes release enormous quantities of gases from deep within the interior. Chemical reactions between rocks and the atmosphere quietly remove some gases while releasing others. Oceans dissolve certain gases before slowly returning them to the air. Every component participates in a continuous exchange that may continue for billions of years. Volcanoes deserve special attention because they act almost like planetary breathing systems. Deep beneath the surface, heat slowly melts portions of the rocky mantle, allowing magma to rise toward the surface. Along with molten rock come gases that have remained trapped underground since the planet formed. Water vapor, carbon dioxide, nitrogen, sulfur compounds, and many other substances escape into the atmosphere during eruptions. Although volcanic eruptions can appear destructive on human timescales, they have helped build and maintain Earth's atmosphere throughout geological history. A distant planet orbiting a red dwarf may experience similar volcanic activity. If its interior remains warm and active, fresh gases can continuously replace at least some of those gradually lost to space. This natural renewal becomes especially valuable during the first few 100 million years, when the parent star is often at its most energetic. Gravity also quietly assists in protecting an atmosphere. Larger planets generally hold on to gases more effectively because their stronger gravitational pull makes it more difficult for fast-moving molecules to escape into space. Earth has retained a substantial atmosphere for billions of years, while the much smaller Mars gradually lost much of its own. This difference reminds scientists that planetary size is just as important as stellar behavior when evaluating long-term habitability. Temperature plays an equally important role. Gas molecules move faster when heated. If the upper atmosphere becomes extremely hot, some of its lightest atoms may eventually reach escape velocity and drift permanently into space. Hydrogen escapes most easily because it is the lightest element in the universe. Over immense spans of time, this slow leakage can influence the composition of an atmosphere, particularly if water molecules are broken apart by energetic radiation. The hydrogen may escape while oxygen remains behind, gradually changing the chemical balance of the planet. Clouds quietly contribute to atmospheric survival in ways that are easy to overlook. Thick cloud layers reflect a portion of incoming light back into space, helping prevent excessive heating of the lower atmosphere. At the same time, they trap heat rising from the surface, especially during colder periods. This balancing act allows climates to remain more stable than they otherwise would. On planets orbiting red dwarfs, where one side may receive constant illumination, persistent cloud systems could become an important part of maintaining long-term habitability. The composition of the atmosphere also shapes the experience of anyone standing on the surface. Earth's air is mostly nitrogen, with oxygen making up a little over 1/5 of the total. Tiny amounts of carbon dioxide, water vapor, and other gases have enormous effects on climate despite their small concentrations. A planet around a red dwarf might possess a very different mixture. Higher amounts of carbon dioxide could provide additional warming. Different trace gases might tint the sky in unfamiliar colors or influence the formation of clouds unlike any seen on Earth. Pressure is another invisible but essential ingredient. Water remains liquid only within certain ranges of temperature and pressure. If atmospheric pressure becomes too low, liquid water struggles to exist at the surface, even if temperatures appear suitable. Earth benefits from an atmosphere thick enough to allow rivers, lakes, and oceans to remain stable. Similar conditions may develop on distant rocky worlds if enough gas accumulates during planetary formation and continues being replenished over time. Scientists have become increasingly optimistic because computer simulations show that many rocky planets may retain their atmospheres more successfully than once believed. Even after periods of intense stellar activity, a combination of volcanic outgassing, gravity, magnetic protection, and atmospheric chemistry may preserve substantial amounts of air. Every factor works together, creating a system far more resilient than any single process alone. The atmosphere also serves as an extraordinary filter for light. Much of the radiation arriving from a red dwarf never reaches the ground directly. Instead, it is absorbed, scattered, or reflected long before touching the surface. This means that the sky experienced by living organisms may differ greatly from the light emitted by the star itself. Sunlight filtering through layers of gas, clouds, and tiny airborne particles could create soft crimson mornings that never truly become bright midday, or gentle amber landscapes beneath skies glowing with subtle shades unknown on Earth. For life, this protective blanket offers more than comfort. It creates stability. Temperatures remain within manageable ranges. Water continues cycling between oceans, clouds, and rainfall. Harmful radiation is reduced before reaching the ground. Winds distribute warmth across continents. Weather gradually shapes mountains, valleys, and coastlines. Every familiar process that supports life on Earth depends, in one way or another, upon the quiet presence of the atmosphere. Perhaps this is why astronomers become so excited whenever they discover a rocky planet orbiting within the habitable zone of a nearby red dwarf. The planet itself is only the beginning of the story. The greater mystery is whether it has managed to keep the invisible veil surrounding it. If that atmosphere has endured through the energetic youth of its parent star and settled into billions of years of quiet stability, then beneath its protective sky, there may be oceans reflecting a crimson sun, clouds drifting endlessly across unfamiliar horizons, and landscapes where life has patiently adapted to one of the most enduring environments the universe can offer. When people imagine another habitable world, they often begin by picturing its land. Mountains rise toward unfamiliar skies, forests spread across rolling hills, and rivers wind through broad valleys. Yet, on Earth, it is not the continents that control the planet's climate. It is the oceans. Covering more than 2/3 of our world, they quietly absorb heat, transport energy across vast distances, feed the atmosphere with moisture, and shape nearly every weather system we experience. Without them, Earth would be a far harsher and far less stable place. A planet orbiting a red dwarf may depend on its oceans even more than Earth does, because many of these planets are likely to orbit very close to their stars. The distribution of heat becomes one of the greatest challenges. If warmth remained fixed only on the side facing the star, enormous temperature differences could develop. Fortunately, water has a remarkable ability to solve this problem through slow and continuous movement. Water stores heat extremely efficiently. Anyone who has visited a beach has probably noticed that the sand becomes hot much faster than the sea during the day. After sunset, however, the opposite happens. The sand cools quickly, while the water remains relatively warm long into the evening. Oceans perform this same quiet balancing act on a planetary scale. They resist sudden changes in temperature, helping create climates that evolve gradually rather than dramatically. Imagine a vast ocean stretching across the day side of a tidally locked planet. For countless years, it receives the steady glow of its nearby red star. The upper layers slowly warm, while deeper waters remain cooler. Winds blowing across the surface begin pushing this warm water toward the darker regions of the planet. At the same time, colder water from the night side gradually returns beneath the surface, creating immense circulation systems that never truly stop. On Earth, ocean currents such as the Gulf Stream transport enormous quantities of heat across thousands of kilometers. These currents help explain why certain regions experience milder climates than their latitude alone would suggest. Similar currents on a red dwarf planet could become even more significant. Instead of following the familiar pattern of changing seasons, they might establish nearly permanent routes, carrying warmth from the endless daylight into regions where the star never rises. These oceans would also become the planet's greatest source of clouds. Wherever sunlight warms the sea, evaporation quietly lifts water vapor into the atmosphere. The vapor itself is invisible, but as it rises into cooler air, it condenses into tiny droplets, forming clouds that drift high above the surface. On Earth, this cycle happens continuously, driven by the daily rhythm of sunrise and sunset. On a tidally locked world, however, the pattern could become much more stable. Above the brightest part of the day side, warm air rises almost constantly. This upward movement encourages the formation of thick cloud layers that may remain in roughly the same region for millions of years. These clouds perform an important service. By reflecting part of the incoming light back into space, they reduce the amount of energy reaching the surface below. In effect, the planet creates its own natural sunshade. This feedback mechanism fascinates climate scientists because it allows some planets to remain cooler than simple calculations would predict. A world receiving slightly too much stellar energy might still avoid overheating if extensive cloud systems continuously reflect enough light away. Nature often balances itself through such subtle interactions. where one process gently compensates for another. Rain becomes another essential part of this global system. As clouds grow heavier with moisture, droplets emerge until gravity draws them back toward the surface. On Earth, rain nourishes forests, fills rivers, and replenishes lakes. Similar rainfall on a red dwarf planet could maintain enormous freshwater systems, carving valleys through ancient rock over hundreds of millions of years. The rivers themselves would become quiet conveyors of change. Beginning in rainy highlands or mountainous regions, they would carry dissolved minerals toward the oceans, slowly reshaping entire continents grain by grain. Even on a planet where the star never moves across the sky, landscapes would never remain completely still. Water would continue sculpting the land with extraordinary patience. Near the twilight belt, where warm and cool air continuously meet, weather may become especially interesting. This broad transition zone could host frequent cloud formation, as moist air from the day side cools while moving toward the night side. Gentle but persistent rainfall might nourish fertile plains stretching around the entire planet like a continuous ring. If forests developed there, they could form one of the largest uninterrupted ecosystems imaginable, circling the globe beneath an eternal sunset. The night side presents its own possibilities. Although it receives no direct starlight, heat carried by both the atmosphere and the oceans may prevent complete freezing across large areas. Coastal regions might remain surprisingly mild, while inland areas become colder. Vast fields of ice could cover portions of the landscape, yet beneath that frozen surface liquid water might continue flowing slowly toward the sea. In some places, warm ocean currents arriving from the day side could keep entire coastlines free from ice, despite the permanent darkness above. Mist would rise where relatively warm water meets colder air, creating mysterious shorelines where visibility changes constantly. Snow might fall gently into the sea before melting almost immediately upon contact with the warmer water below. Storms on such a planet would differ from those on Earth because they would not be driven by alternating day and night. Instead, they would arise from the permanent contrast between the illuminated hemisphere and the dark hemisphere. Winds might flow in predictable directions for centuries at a time, while enormous storm systems slowly travel around the boundary, separating warm and cool regions. Despite this apparent predictability, local weather would remain wonderfully varied. Mountains would redirect winds, valleys would trap cool air, large lakes would influence nearby temperatures, coastlines would experience sea breezes much like those on Earth. The familiar complexity of weather would still exist, even under a sky where the star never changes its position. Climate is also shaped by the planet's rotation, its continents, and its geological activity. If large mountain ranges cross the twilight belt, they could force moist air upward, creating rainy slopes on one side and dry landscapes on the other. Volcanoes might occasionally release ash high into the atmosphere, temporarily cooling certain regions before natural processes gradually restored the previous balance. Over billions of years, oceans quietly become historians. Every wave records the influence of gravity, wind, and climate. Every current carries information about the distribution of heat across the planet. Every layer of sediment settling on the seafloor preserves tiny clues about ancient environments. If intelligent beings eventually evolved on such a world, much of what they learned about their planet's history might come from studying the oceans beneath their ships rather than the stars above their heads. Perhaps the most comforting thought is that oceans rarely hurry. They move with remarkable patience, following rhythms measured not in hours, but in centuries and millennia. Their slow circulation creates stability, and stability provides opportunities for life. Around a red dwarf, where the parent star may shine for trillions of years, the partnership between oceans, clouds, and climate could continue almost without interruption, creating one of the most enduring environments in the entire galaxy. Beneath a soft crimson sky, waves may have been rising and falling for billions of years already, quietly preparing a world where life has all the time it could ever need to grow. A planet may have deep oceans, a comfortable temperature, and a thick atmosphere. Yet another invisible feature can quietly determine whether those advantages endure across billions of years. That feature is the magnetic field. It cannot be seen with ordinary eyes. It has no color, no sound, and no smell. Mountains do not reveal its presence, and oceans flow without acknowledging it. Yet this silent shield stretches far into space, constantly protecting the world beneath it from an endless stream of energetic particles arriving from its parent star. On Earth, it is easy to forget that we live inside an invisible magnetic bubble. Every second, the sun sends charged particles racing outward in every direction. This continuous flow is known as the solar wind. It is not a wind in the familiar sense. There is no air moving through space. Instead, it is a stream of tiny electrically charged particles traveling at extraordinary speeds. If Earth had no magnetic field, many more of these particles would strike the upper atmosphere directly, gradually changing it over immense periods of time. The source of Earth's magnetic field lies deep beneath our feet, thousands of kilometers below the surface. The planet contains an enormous outer core made primarily of liquid iron mixed with other heavy elements. This molten metal is constantly moving because of the heat escaping from Earth's interior. As the planet rotates, these slow-flowing currents generate powerful magnetic fields through a process that scientists often compare to a gigantic natural electrical generator. The result is a protective field extending tens of thousands of kilometers into space. Although completely invisible, this magnetic field has a shape that can be imagined rather easily. On the side facing the sun, it is gently compressed by the constant flow of charged particles. On the opposite side, it stretches into a long tail extending far beyond the moon's orbit. Earth travels through space wrapped inside this protective cocoon, carrying every ocean, forest, desert, and city safely within its embrace. When charged particles encounter this magnetic field, many of them are gently guided around the planet rather than striking the atmosphere directly. They follow the invisible magnetic lines, much as leaves floating on a river follow the direction of the current. Only near the polar regions do some of these particles manage to travel downward into the upper atmosphere. There they collide with atoms of oxygen and nitrogen, producing the shimmering curtains of light known as the aurora. Imagine standing beneath the night sky of Earth as green ribbons slowly ripple across the horizon. The display appears peaceful and beautiful, yet it is actually evidence of a quiet battle taking place far above. The magnetic field has intercepted a stream of particles from the sun, redirecting most of them harmlessly away while allowing a small number to paint the sky with glowing colors. Without this invisible shield, those particles would interact with the atmosphere much more directly. For planets orbiting red dwarfs, the importance of magnetic protection may become even greater. Because these planets usually orbit much closer to their stars than Earth orbits the sun, they are immersed in stronger stellar winds and more frequent bursts of energetic particles. Their atmospheres face a constant challenge. Every flare, every magnetic eruption, and every stream of charged particles attempts, ever so slowly, to carry small amounts of atmospheric gas away into space. A strong magnetic field does not make a planet invulnerable, but it greatly improves its chances of long-term survival. Instead of allowing energetic particles to strike the atmosphere directly across the entire globe, the magnetic field deflects much of that energy around the planet. Over millions and billions of years, this quiet protection may preserve enough atmosphere for oceans to remain liquid and for life to continue evolving. The size of a magnetic field depends on several factors. One of the most important is the planet's interior. A world must remain geologically active for a long time if it is to maintain a liquid metallic core capable of generating magnetism. As planets gradually cool, their internal activity may slow. If the molten core eventually solidifies, the magnetic field can weaken or disappear entirely. Mars offers a fascinating example. Billions of years ago, Mars appears to have possessed a global magnetic field much like Earth's. At that time, rivers flowed across its surface, lakes filled impact craters, and the atmosphere was considerably thicker than it is today. As the Martian interior cooled, however, its magnetic field largely disappeared. Without that invisible protection, the solar wind gradually stripped away much of the atmosphere over immense periods of time. The dry, dusty planet we see today still preserves many signs of its wetter past. This comparison naturally leads astronomers to wonder about rocky planets orbiting red dwarfs. Could they maintain active molten cores for billions of years? The answer depends partly on their size. Larger planets generally retain internal heat longer because their greater volume cools more slowly. Such worlds may continue generating magnetic fields long after smaller planets have become geologically quiet. Tidal forces may also help. Many planets orbiting red dwarfs experience strong gravitational interactions with their parent stars or with neighboring planets. These gentle but continuous gravitational pulls slightly flex the planet's interior, generating additional heat through friction. Jupiter's moon Io demonstrates this process beautifully within our own solar system. Constant gravitational stretching keeps its interior extraordinarily active, making it the most volcanically active world known. On a rocky exoplanet, similar tidal heating could help maintain a molten core capable of sustaining a magnetic field over astonishing spans of time. Even if the magnetic field is somewhat weaker than Earth's, it may still provide meaningful protection. Combined with a thick atmosphere, extensive oceans, and ongoing volcanic activity, it becomes part of a larger network of systems that support planetary stability. No single feature determines whether a world remains habitable. Instead, each contributes quietly to an intricate balance that develops over billions of years. If intelligent observers eventually evolved on such a planet, they might discover magnetism long before understanding its true importance. At first, they would notice that certain minerals always point in the same direction. They might use simple magnetic compasses to navigate across oceans and deserts without realizing that the force guiding their instruments originates deep within the planet itself. Only much later would they understand that the same invisible phenomenon protecting their ships also shields their entire atmosphere from the restless activity of their small crimson sun. From space, their planet might appear wrapped inside delicate arcs of glowing particles whenever the parent star released a powerful flare. These invisible magnetic lines would quietly redirect enormous amounts of energy, allowing forests to continue growing, rivers to continue flowing, and oceans to continue reflecting the soft reddish light above. Most living creatures would never notice the silent guardian surrounding their world. The remarkable thing about magnetic fields is that they ask for no recognition. They perform their work continuously without changing the appearance of mountains or altering the color of the sky. Yet, across unimaginable stretches of time, they may preserve the very conditions that allow life to exist. Around a red dwarf, where the nearby star can occasionally awaken with bursts of magnetic energy, the planet's own magnetic shield becomes an equally patient companion, standing watch through billions of years of quiet cosmic history, protecting an entire world with a force that remains almost completely invisible. Wherever we find life on Earth, we eventually find a connection to sunlight. Deep forests, open grasslands, tropical islands, quiet ponds, and even tiny patches of moss growing between stones all depend, directly or indirectly, on plants and other organisms that capture light. Every leaf quietly performs one of the most remarkable transformations in nature. It takes energy arriving from a star nearly 150 million kilometers away and uses that energy to build the living world around it. When we begin imagining life around a red dwarf, one fascinating question naturally appears. Could plants perform the same miracle beneath a star whose light is so different from our own sun? At first, the answer may seem uncertain. After all, A red dwarf emits much of its energy in deep red and infrared wavelengths rather than the bright visible light that dominates sunlight on Earth. Human eyes cannot even see much of that radiation. It might seem reasonable to wonder whether photosynthesis, the process plants use to capture energy, could function under such unusual conditions. The encouraging answer is that photosynthesis is remarkably flexible. On Earth, plants do not use every color of sunlight equally. The familiar green leaves covering forests actually reflect much of the green light that reaches them, which is why they appear green to our eyes. Instead, they absorb large amounts of red and blue light, because those wavelengths are especially useful for driving the chemical reactions that produce sugars and oxygen. This simple observation immediately makes red dwarfs more interesting, since these stars naturally produce abundant red light. At least part of the energy required for photosynthesis is already available. The exact chemistry might differ from that of Earth's plants, but the basic principle remains the same. Light carries energy, and life has an extraordinary ability to find ways of using whatever energy is available. Nature on Earth already demonstrates this adaptability in countless ways. Not every plant grows beneath bright open skies. Some spend their entire lives beneath the dense canopy of ancient forests, where only a small fraction of sunlight reaches the ground. Others grow in caves near small openings, along shaded cliffs, or beneath floating layers of aquatic vegetation. These plants have evolved pigments that allow them to capture even very limited amounts of light with surprising efficiency. Certain microorganisms take this adaptability even further. In oceans, bacteria live at depths where sunlight has become extremely faint. Some species specialize in absorbing wavelengths that ordinary plants barely use. Others rely on pigments completely different from chlorophyll. Their existence reminds scientists that evolution is not limited to one solution. If a source of energy exists, life often discovers creative ways to harvest it. On a planet orbiting a red dwarf, photosynthetic organisms might gradually evolve pigments designed specifically for reddish light. Instead of the bright green chlorophyll that dominates Earth's landscapes, entirely different molecules could become common. Forests might appear deep purple, almost black, dark blue, or rich burgundy because darker pigments absorb more of the available light instead of reflecting it away. Imagine walking through such a forest. The leaves overhead would not shimmer with familiar shades of green. Instead, they might absorb nearly every ray of crimson sunlight falling upon them, giving the entire landscape a darker, almost velvety appearance. To human eyes, the forest could seem mysterious, yet to the native plants, every leaf would be functioning with remarkable efficiency, quietly collecting the energy needed for growth. The atmosphere would influence these colors as well. As sunlight passes through layers of gas and clouds, certain wavelengths are scattered more than others. Earth's atmosphere produces brilliant blue skies because shorter blue wavelengths scatter more easily than red ones. A different atmosphere beneath a red dwarf could produce entirely different lighting conditions, encouraging plants to evolve pigments suited to that particular environment. The amount of available light also shapes plant architecture. On Earth, trees growing in dense forests often develop tall trunks in an effort to reach brighter sunlight above the canopy. In open fields, many plants remain short because light is already abundant. Around a red dwarf, where the overall brightness may be lower, plants could develop broad leaves with enormous surface areas to capture as much light as possible. Every square centimeter of leaf would become valuable. Some plants might even grow unusually slowly. Earth already contains trees that live for thousands of years, while adding only tiny amounts of new wood each season. On a world illuminated by the gentle glow of a red dwarf, evolution might favor patience over speed. Instead of racing upward, forests could mature gradually over centuries, producing landscapes of incredible age where individual trees remain alive longer than many human civilizations have existed. Water availability would influence these ecosystems just as strongly as light. Where rainfall is frequent, enormous forests may spread across the twilight belt, nourished by constant moisture carried from nearby oceans. Along drier regions, smaller shrubs or hardy grasses might dominate. In permanently illuminated areas receiving steady warmth, dense vegetation could cover wide plains, while colder regions nearer the night side support only scattered mosses, lichens, or specialized cold-tolerant plants. Flowering plants, if they evolved, might not follow the daily rhythms familiar on Earth. Here, many flowers open at sunrise and close after sunset, guided by an internal biological clock synchronized with changing daylight. On a tidally locked planet, such signals would hardly exist. Instead, flowering might depend on rainfall, seasonal temperature changes, nutrient availability, or entirely different environmental cues. The interaction between plants and animals would also evolve in fascinating ways. Pollinating insects might navigate using the constant position of the star rather than the movement of the sun across the sky. Flying creatures could orient themselves toward the permanently illuminated horizon. Fruits might ripen according to long climatic cycles rather than changing day lengths. Every familiar ecological relationship would continue, but each would adapt to a sky unlike any experienced on Earth. If intelligent observers from Earth visited one of these forests, they might initially think the vegetation appeared unhealthy because of its unusually dark colors. Yet scientific instruments would reveal something extraordinary. Every leaf would be quietly capturing the reddish light of its parent star with remarkable efficiency, converting it into the chemical energy supporting entire ecosystems. Oxygen production might continue much as it does on Earth if photosynthesis follows similar chemical pathways. Forests would slowly release oxygen into the atmosphere while absorbing carbon dioxide, helping regulate the planet's climate over geological time. The very air surrounding these alien landscapes could become breathable, not because it resembles Earth's history, but because life once again discovered an elegant partnership with its star. Perhaps the most beautiful thought is that these forests would grow beneath a sun that never rises and never sets. Leaves would never experience the sudden arrival of morning or the fading light of evening. Instead, they would spend every moment beneath the same quiet crimson glow, gently collecting energy year after year, century after century. The forests themselves might become symbols of extraordinary patience, rooted beneath one of the longest living stars in the universe, quietly transforming soft red light into living worlds that endure almost as long as the stars that nourish them. Once plants begin covering the surface of a planet, an entirely new chapter of natural history quietly unfolds. A single leaf rarely exists alone. Around every forest, meadow, marsh, or coastline, countless relationships begin to develop. Tiny organisms feed on plants. Larger animals feed on them in turn. Fungi recycle fallen wood dust. Insects pollinate flowers. Microorganisms enrich the soil. Rivers carry nutrients from mountains to the sea, where entirely different ecosystems emerge. Life gradually weaves itself into an intricate network in which every living thing influences many others. On a planet orbiting a red dwarf, this same process may occur. Yet beneath skies illuminated by the soft crimson glow of a small and patient star, the first ecosystems would almost certainly be simple. On Earth, for billions of years, life consisted only of microscopic organisms living in oceans and shallow coastal waters. Complex forests and large animals appeared much later. A similar progression may unfold around a red dwarf. Tiny photosynthetic organisms could slowly spread across worn shorelines, forming colorful microbial mats that gently capture the star's reddish light. These thin living carpets would quietly release oxygen and produce organic material, laying the foundation upon which every future ecosystem depends. As more organisms evolve, diversity naturally increases. Different species begin specializing in different environments. Some prefer warm coastal waters, while others thrive in cool mountain streams. Certain organisms settle on rocky cliffs constantly bathed in twilight, while others adapt to humid forests where thick clouds soften the already gentle light. Over millions of years, every habitat becomes home to communities uniquely suited to its particular conditions. The twilight belt may become especially rich with life. Here, moderate temperatures, reliable rainfall, and comfortable lighting combine to create remarkably stable environments. Vast forests could circle the entire planet like an endless green, purple, or nearly black ribbon separating permanent daylight from permanent night. Rivers flowing from warmer regions might cross these forests before gradually disappearing beneath glaciers on the colder side of the world. Along every riverbank, life would quietly flourish. Imagine walking through one of these forests. The air is cool and pleasantly humid. Massive trees rise toward a sky glowing with permanent sunset colors. Their broad dark leaves absorb nearly every ray of crimson light filtering through the canopy. Mosses blanket ancient stones. Small streams weave silently between enormous roots polished smooth by countless centuries of flowing water. Every surface seems alive with tiny organisms quietly performing their own role in the ecosystem. The sounds of such a forest may differ from those on Earth. Birds, if they exist, would not announce the arrival of dawn because dawn never comes. Instead, songs might follow entirely different rhythms based on seasonal temperature changes, approaching storms, or social communication within their own communities. Insects may produce gentle sounds throughout much of the day because there is no nightly darkness signaling a period of silence. The forest could possess a continuous, peaceful chorus that slowly changes with weather rather than with sunlight. Animals themselves might evolve in fascinating directions. Eyes adapted to reddish illumination could become larger, allowing more light to enter. Some creatures may develop exceptionally sensitive vision capable of detecting wavelengths that humans cannot easily see. Others might rely less on sight altogether, favoring hearing, smell, or subtle vibrations carried through the ground. Evolution never insists upon a single solution. Instead, it quietly experiments with countless possibilities across immense spans of time. Predators and prey would continue their ancient relationship, but even this balance might look different beneath constant lighting. On Earth, many hunting strategies depend upon the changing brightness between day and night. Around a red dwarf, camouflage would become even more important. Dark leaves, reddish shadows, and softly glowing landscapes could encourage remarkable patterns of coloration. Animals might blend perfectly with tree bark tinted by crimson light, or disappear among rocks, reflecting the warm colors of the endless horizon. Near the boundary between the twilight belt and the night side, another kind of ecosystem may appear. Here, temperatures become cooler, and sunlight weakens steadily. Hardy plants gradually replace dense forests. Thick mosses, low shrubs, and specialized fungi may dominate the landscape. Streams remain unfrozen because warm groundwater continues feeding them from below, while nearby hills remain covered with snow that never completely melts. Further into the permanent darkness, photosynthesis may eventually become impossible on the surface. Yet this does not necessarily mean life disappears. Earth already demonstrates that sunlight is not the only source of energy capable of supporting living organisms. Deep beneath our oceans, hydrothermal vents release mineral-rich water heated by volcanic activity. Entire ecosystems flourish around these vents, despite existing in complete darkness thousands of meters below the surface. Similar environments could exist beneath the night side of a red dwarf planet. Underground caves warmed by geothermal heat might shelter unique communities of microorganisms. Small animals could feed upon bacterial colonies growing around mineral-rich springs. Beneath thick ice, covering frozen lakes, liquid water may continue circulating slowly, supporting ecosystems entirely hidden from the sky above. The oceans themselves would become worlds of astonishing diversity. Shallow coastal waters bathed in constant reddish light could support vast underwater forests of photosynthetic organisms unlike anything on Earth. Deeper waters gradually fade into darkness, where bioluminescent creatures may evolve to communicate, attract mates, or lure prey. Tiny flashes of blue-green or violet light drifting through the deep sea would create silent underwater constellations beneath the already unfamiliar heavens. Storms would also shape these ecosystems. Strong winds crossing the twilight belt might occasionally bring heavy rainfall, flooding river valleys before retreating once more. Plants would adapt flexible roots capable of surviving temporary flooding. Animals might migrate short distances following changing weather patterns rather than changing seasons. Entire ecological cycles would revolve around moisture, temperature, and atmospheric circulation instead of sunrise and sunset. One especially interesting possibility involves extremely long-lived organisms. Since red dwarfs themselves remain stable for astonishing lengths of time, evolution may favor species that grow slowly but survive for centuries, or even millennia. Enormous trees might add only a thin ring of growth every few years while gradually reaching extraordinary sizes. Coral-like reef builders could quietly expand across shallow seas for hundreds of thousands of years, creating underwater landscapes visible even from space. Fungi may become equally impressive. On Earth, some fungal networks already stretch across many square kilometers beneath forests, quietly transporting nutrients between trees. Around a red dwarf, similar underground networks might persist for incredible lengths of time, connecting entire ecosystems into vast living webs hidden beneath the soil. Individual organisms could survive far longer than humans typically imagine, slowly growing beneath landscapes that appear unchanged from one century to the next. If intelligent beings eventually emerged within these ecosystems, they would inherit a world defined by remarkable stability. Entire forests may remain recognizable across thousands of generations. Rivers would continue following familiar paths carved over millions of years. The crimson star would shine from the same position in the sky that it occupied when the earliest ancestors first learned to observe the world around them. Such ecosystems remind us that life does not require a perfect copy of Earth. It requires energy, water, time, and the opportunity to adapt. Around a red dwarf, every one of those ingredients may exist in abundance. Beneath quiet crimson skies, nature could patiently construct forests, oceans, mountains, and living communities unlike any found in our own solar system, yet governed by the same universal principles that have guided life on Earth since its earliest beginnings.